So here is supernova 1987A. It was observed first on January 23rd, 1987, which was 30 years ago this year, and 2017. And it was discovered by some Canadian astronomers who happened to catch it just it was starting to brighten. So this is the only supernova that we have ever observed from the beginning stages through the middle stages and right through the collapse and after the collapse. So we've seen it pre-collapse, we saw the collapse, and we've been studying it ever since after the collapse. The puzzle about supernova 1987A, even though it's the first one we detected and observed and studied, it did not fit the model that had been developed for what a typical type 2 supernova event should look like. It has a dense ring of material around it that was ejected from the star about 20,000 years before the collapse. And that ring is about a light year in diameter, glows brightly in optical light. The center structure is about a half a light year in diameter, and there are two huge clumps of debris in the center moving away from each other at about 2 million miles per hour. And this expanding ring, there's an expanding ring, besides the optical, an expanding ring of X-ray emission that moved through the ring as the shock wave from the collapse moved through the material that had been ejected from the star while it was undergoing its collapse. And these X-ray emissions, they have been able to observe them as they've moved further and further and further away from the center of the collapse and got very, very bright. And it kept getting brighter and brighter and brighter until 2013, and they've been sort of constant since then. So that is evidence that the shock wave has moved through all the gas and dust that's been ejected during the collapse of the star and has now moved into the interstellar medium surrounding the entire supernova remnant. So that progenitor star, the collapse of that produced prodigious amounts of dust that are in the way, but and that is, of course, how that we think all the dust got there from the very beginning, from these supernova events that allows the continuing of more and more stars to form because of the incredible amounts of material that are created during these kinds of events. And so far, though, the interesting part about this is that there was a flash of neutrinos during the collapse, which led the scientists to believe that it was either a neutron star or a black hole that would produce that. However, so far, there's absolutely no evidence of a stellar core, so they still do not know what kind of stellar core is in the center of 1987A, even though they have been observing it for 30 years. And that is, this particular image shows 1987A and the rings of material in that hourglass configuration that moved away from the center of the collapse. Assassin 15LH is a supernova event that took place about 3 billion light years away. It's twice as powerful as any previous supernova event. And it has also a mystery associated with it. 3 months after the light started to fade from this particular event, all of a sudden the ultraviolet radiation started increasing 5-fold, and it stayed that much brighter than the rest of the emissions from this event for 2 months, and then it started again to slowly fade away over time. Well, what could possibly have caused the UV to increase 5-fold while the optical continued to fade? There's not enough radioactive nickel to have produced that kind of brightening. If the shock wave had been moving, if it was produced by the shock wave, either moving through the ejecta or something outside of the remnant itself, it would have produced a very unique set of emission spectra that was not observed whatsoever. So again, a reasonable explanation of most of what they've observed with this particular event would lead one to believe it might be a magnetar, again, with that really strong field. However, even that does not explain the resurgence of the ultraviolet radiation. So again, that one is, again, another puzzle. This graph shows that there are a couple of magnetar models, Assassin 1511H being the one at the top. So it does fit a model for a mathematical modeling of a light curve with a magnetar as part of the event. But you will see, look at the difference between that and supernova 1987A, which is the green line at the bottom of this graph, just to give you an idea of the amount of power in this particular event. These two pulsars, Geminga and PSR B0355, look completely and totally different from each other. These are Chandra data is blue and purple, the X-ray data. There's some Spitzer infrared data added to this also, but mostly we're looking at X-ray data. Underneath the data are illustrations of these two pulsars, and you can see that the configuration of them are completely and totally different. Geminga was discovered first as a really bright object in gamma rays. And BO355 is really bright in radio waves. But Geminga doesn't show any radio, and BO355 doesn't show any gamma ray. So using the Chandra data, they plotted the shape of the wind pulsar that surrounds the pulsar itself. Some of the really energetic pulsars create a wind nebula around them, the PWN, the pulsar wind nebulas. And both of these two pulsars have that. So the toroid structures caused by the wind nebula causes that toroid structure to be distorted and the jets to be distorted. And the distortion is because both of these pulsars are moving at really high rates of speed through the interstellar medium. And whatever, of course, the medium that they're surrounding them is different from each other. So the material is either denser or less dense or more dense. And so there are different amounts of forces on the nebulas and on their jets. So that changes the orientation of them. So the reason that you do not see radio from Geminga or gamma ray from BO355 is because those emissions have been oriented in a different direction away from our line of sight. They are still emitting them, we just can't see them in our direction from our perspective here on Earth. M82 X-2 is another pulsar. It is located in the M82 galaxy, which is about 12 million light years away. It is what is known as a ULX, an ultra-luminous X-ray source. This pulsar rotates once every 3.7 seconds and revolves around a companion star about 5.2 solar masses, and it's in a binary system. It was thought to be a black hole, but now it has been determined to be the brightest pulsar ever recorded. The composite image here is Chandra X-ray data in blue, the new star data is in purple, also X-ray, and the optical image is from NOAO, and that's the gold color. It was the new star mission that detected some really odd pulsations associated with the pulsar. They detected the pulsations, so then they went to the Chandra data observations, and that used that to determine the location of those pulsations, and therefore the location of the actual pulsar itself emanating those pulsations. X-ray binary Circinus X1 is an X-ray binary system of a neutron star and a massive companion. clouds of gas and dust have formed 4 separate rings around Circ X1. This is a composite image with Chandra X-ray data and optical data from the digitized sky survey. It shows the ring structure. That ring structure are light echoes. Light echoes are just radiation from the star, X-ray radiation from the stellar core that is bouncing off those 4 different rings of debris and being redirected towards us here on Earth. So when you have that kind of a light echo configuration, you can use that to determine the distance, to measure the distance to it in a fairly accurate way. So Chandra data was combined with radio data from Australia to measure the distance to Circ X1. And the result of that measurement was that it's 30,700 light years away, which caused a little bit of a change in thought, because that calculation puts it twice as far away as it was thought to be. So if it's twice as far away, then it has to be twice as bright. If it's that bright, then it's outputting so much radiation that it is going to mess up the Eddington limit. The Eddington limit is simply that balance between gravity in and radiation out, and if the only thing that's thought to exceed that limit would be a black hole. So and the particles that are coming from the center are moving at 99.9% of the speed of light. So with that extreme of a velocity for the particles coming from the center, with that measurement of distance, and because of the Eddington limit, it is thought that there must be a black hole associated with the center of this.